Hello, this is the second chapter of the course, and in this chapter we are going to continue to discuss the identification issue. And one of the most important identification failures in econometrics is the endogeneity problem. So endogeneity is in the previous lecture, in the previous chapter, I explained what is an identification argument, and also I gave you an example of identification failure, the multicollinearity. So multicollinearity is maybe the easiest way, a very simple problem because it's easy to detect and easy to solve. So, but the second example of identification failure is the endogeneity, which is more important and more difficult to fix, but it's also very critical in your analysis. So let's think about the classical linear regression model again. We have four assumptions, and the fourth assumption is not used in identification. So basically, we have three explicit assumptions plus implicit basic assumptions. And in this case, if the full rank condition is violated, that is the multicollinearity problem. But if the exogeneity assumption is violated, that is the endogeneity we are going to discuss in this chapter. By the way, 0 subscript k means k-dimensional vector of zeros. So it's not simply 1, 0, but 0, 0, 0, 0 vector, 0 vector. And as I said, we are going to consider what happens if x and epsilon are correlated. They are not uncorrelated. So and then using the definition of exogeneity, x is correlated with epsilon at a term. So often we say x is endogenous. That's why the problem is called the endogeneity problem. Before talking about the endogeneity problem, I would like to discuss one subtle distinction between two different concepts. Also, it is very subtle and it's really not easy to explain, but it's important. But no textbooks consider and discuss this enough, I think. So let me try this. So what I'm going to tell you is there are two different approaches to the regression model or any type of econometrics or economics model. One is the reduced form approach and the other is the structural form approach. Here, let's restrict our attention to the regression model, linear regression model. And if you take the reduced form approach, you are basically, what you are doing by the regression model is just approximating y. You are approximating the dependent variable y by a linear function of x. That's the regression. If you take the regression in this way, that is the reduced form approach. And as usual, just we take y and x given as observed variables. And the only assumption in this case, the only assumption you use is this: x prime, expected value of x prime, x transpose is invertible. The full rank condition. The same full rank condition, as long as this is satisfied, you can calculate this. It's easy. So if you have a large number of observations on x and y, then you can calculate the expected value of x and y very accurately, and you can calculate expected value of x transpose and then take their inverse. And we are going to define this guy as beta. So far there is no problem. As long as you can calculate this, it is not it's obvious. So it is just a matter of calculation. And then what is this? So this is one possible approach to the regression model. What is this? Mathematically, there are arguments that justify this approach. What we are doing here is you are doing linear projection of y on x. So y is projected onto the linear space spanned by x. If you don't understand what I'm saying, don't worry. Just in case, if you understand, that would be great. Then it will help you a lot. So it is just a projection. It's projection. I don't know why you are projecting y on x. So, but that's possible. So you can do it for whatever y and whatever x, as long as the full rank condition is satisfied. So that means, in other words, without knowing what's the relationship between x and y, you can do this. You can approximate. So that's how you interpret the regression model. And then, so you are approximating y by x prime beta. X transpose beta is your approximation of y using this form. And then the approximation error will happen. There will be approximation errors. And we define that as epsilon, which is y minus x transpose beta. So you predict y with x beta, but there must be difference, and that's epsilon. So in this case, epsilon is just a residual, and epsilon does not have its own meaning. It is just residual. You just approximated y, but it was not correct enough, then you always get some residual. That's the meaning of that. And then, by definition, so according to our definition, epsilon is defined in this way. Then it is very easy to show that the residual epsilon is always uncorrelated with x. No matter what x is, no matter what y is, as long as the full rank condition is satisfied and as long as you define beta that way, define epsilon that way, then your epsilon will be uncorrelated. So in this case, as you see, this is not our approach. In the previous chapter, I already used a different approach, but this is interesting. So in this case, exogeneity is not an assumption. It is always true by definition, and the only assumption is full rank assumption, which is also very easy to check. Let's think about this example. Suppose that y is the number of COVID confirmed cases in the United States, and x is the S&P 500 stock market return. So you may regress whatever on whatever variables. So regress COVID confirmed cases on S&P 500. So, and you may know last year in 2020, COVID confirmed cases in the United States increased drastically, and at the same time, the stock market increased drastically. So if you regress y on x, you are going to get a very strongly positive relationship between them. So x may predict y very well. All right, both are increasing like together like this. So approximation, I didn't do it, but I guess approximation will be very good for absurd reasons. However, no one is going to interpret this. So suppose that when the stock market increases by 1% point, say COVID cases increase by 2% point, for example. But it doesn't imply if you, like for example, suppose that the president or the government closes all the stock market exchanges, then will it help to to mitigate the confirmed cases? Of course not. So increasing in S&P 500 may help approximate the COVID cases just retrospectively. Now, after 1 year, so if you look back, it looks like they may be correlated, but it does not imply S&P 500 caused COVID or vice versa. So in this case, literally you are just approximating without any background, without anything. it is not bad. Sometimes you need to do this. Like for example, when you predict something, you just want to put all the possible variables, and get the best prediction. But the problem is it is not justified by any theory. And also in this case, epsilon is just an approximation error. Like for example, you cannot interpret epsilon as, for example, like other like say medical situations or other cases. Is not, epsilon is not anything else. It has no meaning by itself. So this is one possible approach. And on the other hand, you can think about the structural approach. This is what I introduced in the previous chapter. So you put assumptions, and then in this case, the key difference here is we assume that beta is the true relationship between x and y. Previously, I don't know what is x and y, what's their relationship, but just use linear approximation because that's easy. That's easy to handle. And linear approximation worked well in our example. So let's do that. But there is no meaning of beta. But here, I'm going to interpret beta as a serious relationship. So say, if you take the previous example, you have to assume that stock market, 1% increase in stock market will cause beta percent increase in the COVID cases. That's your assumption when you take the structural approach. And if those assumptions are satisfied, then we learn that the true relationship beta can be identified. Right? There exists a true value, and you need assumptions, and then from the data you can guess the true value very correctly. That's what we learned in the previous chapter. And in this case, another important distinction is that epsilon is very important. Epsilon is not just a remainder from the approximation. It has its own meaning. For example, as I said, suppose that suppose that COVID cases, the number of COVID cases is affected by two things: stock market return and say like a number of medical steps per population, for example. So if you for some reason, if you believe that there are only two factors, stock market return and medical facilities, and then but you don't observe, suppose that you don't observe the second one in the data, then epsilon is the second factor. So epsilon can take some meaning, like it's an unobserved factor that affects the COVID case. Compare that to the previous interpretation. Here, epsilon is residual. I don't know what that is. That could be like medical things or anything, but I don't care. It has no meaning. But now, in the structural approach, epsilon itself has its own meaning and has its own properties. And so, it's totally different approach, but the problem here is you may think structural approach is superior, but actually not, because you need to make assumptions. So you need to make assumptions, and if one of the assumptions is wrong, all the conclusions will be wrong. Like some may survive, but all conclusions are dangerous. So making more assumptions enables you to make more stronger conclusions, but on the other hand, that means your conclusions are more vulnerable to the potential failure of the assumptions. Example here, typical example, Y is the wage. We would like to explain the wage determination and say X is education and epsilon is intelligence other than education. So your unobserved ability. In this case, this is the starting point. I'm going to put all the meanings at the beginning, and I label Y wage, X education, Y intelligence, and suppose that also assume that wage is determined by these two, and wage is linear in education, and under those assumptions, you would like to identify the additional effect of additional education on wage. In this case, you can say that if you attend school for another year, your wage will increase by beta. It implies education X causes Y. There is cause and effect relationship between X and Y if you take this approach. Okay, I'm going to continue in the next video. It gets too long.